Hi everyone, in this video I'm going to walk you through my TinyRISC-9, a custom 9-bit CPU that I designed and built from scratch using Search and Verilog. We'll talk about some constraints this CPU have and what makes these constraints interesting, and the 3 programs we're able to run using the CPU. We'll also briefly go over the assembly code of these 3 programs as well as the Python assembler. So let's start. So to start, let's talk a little bit about the architectural overview. The main thing about our constraint is size. We want to make a CPU that is very compact and very specialized for these 3 algorithms. If you can see, our instruction width is only 9 bits. For comparison, a standard MIPS CPU or a ARM CPU is 32 bits. So we are given very little instruction bits. Another thing, our data path width is also very small. If you can see, our data path size is 8 bits, so is our register data size path, and our data memory size size are all 8 bits. Now, the key thing here is that in our programs actually support working with numbers that are 16 bits rather than 8 bits. So this actually makes it very interesting because then we have to design our instructions as well as our programs in a way that we're able to divide a singular number and store it in 2 separate registers and also perform operations on those to get a fuller number that is the size of our actual data bit size. Another thing, we're only allowed 8 registers, and also our instruction memory is also very small. We only have 512 instruction size, so that means that all 3 programs must fit in less than 500 slots. There's also only 226 data memory size. We have 2 flags, the carry and borrow flag. The borrow flag is also shared with the sign flag, which we'll talk about more later, and also our branch range, as shown here. So let's talk more about our instruction encoding. So given that we only have 9 bits to work with, this means that we have to design our instruction in a very smart way so that we're not wasting any bits because we have so few. Now, in order to support these 3 programs, we have to have enough instructions. So at first, we would use 4 bits as the instruction opcode, which then allows us to support at least 16 instructions. After that, we have 4 main types of instructions: register to register, intermediate, branch, and special instructions. The register to register would have a 3-bit RD and a 2-bit RS. The intermediate would also have a 3-bit RD but a 2-bit intermediate value. For branch instructions, all 5 remaining bits will be used for the offset, and for special instructions, we have 3 bits of RD and 4 functions, so 2 function bits. So let's briefly talk about these types of instructions. So the first one is our register to register. Register to register, we have in total 7 different instructions, from adding, subtracting, XOR, and multiplication. So to start, one big issue with our original design, or the limitation with our instruction size, is that given that since we use 3 bits to be RD and 2 bits to be RS, that means that some registers can never be source registers, which when designing the function makes it so that some registers are never actually fully utilized. So what we did instead is that we have 2 add instructions and 2 sub instructions, add and add X, and sub X. The main difference between add and add X is that add in this case would support RD would still be the same support register from register 0 to register 7, but the source register would be register 0 to register 3. And add X, on the other hand, would also still have 0 to 7 register for RD, but RS would support the last 4 from R4 to R7. The idea behind this is that by wasting an extra instruction, we're actually able to use these very common instructions, which is adding and subtracting, to be any register. So any registers for adding and subtracting can be source or destination. In XOR and multiplication, on the other hand, we will instead only allow RD to be the first to be RD to be all 8 registers, but RS to only be the first 4. Now, if you see, there's also 2 different types of multiplication functions. The reason behind that is, like I mentioned before, the limitation of our size of our registers. For 2 8-bit values to multiply, the result could be 16 bits. That means that a simple flag of a carry would not suffice. There would be too many remaining. So what we did instead is that we would have 2 types of multiplication function. One that calculates the lower bytes, the last 8 bits, and then the other one calculating the carry high bits, the first 8 bits. So to do this is that then by running 2 multiplication functions, we're actually able to store the full multiplication result in 2 separate registers. The intermediate values are also very standard. And in loading intermediate, we can load numbers from 0 to 3. Add intermediate, we add numbers from 0 to 3, and sub from add 0 to 3. The idea behind these is that with these, we can actually add I and a sub I becomes very good for things like registers that count the for loops, the alliterative registers. And then for add I, it helps us set the base values for a register, like zeros and ones. Now, we also include a shift. In this case, shift actually, there's no point of shifting 0 registers since it doesn't do anything. We would almost always shift by either 1, 2, or 3. The idea of having a shift register is that, let's say we want a register to store a value like 64. If we load and keep adding, it would simply take too much instructions. Remember our limited instruction size. And instruction memory size. So in this case, we can load, let's say, the number 4, and we keep shifting it until it multiplies to 64. In this case, the shift instruction allows us to get these specialized bigger numbers more efficiently. Now, more onto our control floor and memory instructions. We have load and store, which is very similar to our register instructions. In this case, it simply loads from RS or RD, or stores from RS or RD. And the main one we have here is our 2 branch instructions. Number 1 being just an unconditional jump, and number 2 looking at the borrow bit. This is why our sign bit, like I said, we use borrow for sign as well. Now, the reason behind this is that since we have so little instructions, we cannot waste more instructions as comparisons. Now, the most common comparison is taking a jump if one number is bigger than another. This is where we can reuse our sub instruction. If number 1 is smaller than number 2, that means that number 1 subtracted by number 2 must require a borrow bit. So in this case, if we want to do the comparison, we can simply subtract these 2 numbers, check if the borrow bit exists, and then perform the offset. If you look at our special instruction, another one is our sign instruction. This is why the sign instruction also sets the borrow flag. The sign instruction takes a look at a number and checks if it's negative. And if it's negative, it sets the borrow flag to be 1. The idea behind this is that this allows us to do another type of check that will be very useful later on in our programs, is that if a number is negative, we take the jump, the offset jump. The other one, and if you see here, one also very specialized, unique thing we design our offset is that our offsets are always times 2. The reason behind this is, remember, we only have 5 bits to be the offset. This means that it would only support values 32 values. Now, in order for us to be able to jump forwards or backwards, this means that we will need negative and positive offsets. This means that if we only have 5 bits, it would only support a range from negative 16 to 15, which is too little of a jump. So the idea here is that, okay, we are going to limit our instructions so that it can only jump in even numbers, but then it allows us to jump from negative 32 to 31, making it a much bigger jump. Another 3 special instructions, the not instruction, which flips the bits, which will be very useful for a lot of our specialized programs. Pop count, which counts the number of bits in the register, and the done special instruction, which halts and signals the done for the instruction for the program. Now, let's talk about how these functions are now useful for our program. And the first program our CPU supports is the Hamming distance. The Hamming distance essentially looks at two values and checks the biggest bit difference between these two values. Now, like I said, each of these values are going to be assigned 16 bits, and not only there's going to be 2 of them, there's going to be 32 of them. And the idea is that we're going to compare all 32 12-bit value, compare their Hamming distance, and find the biggest and smallest difference. So this is where our functions like XOR and count become very helpful. So the main idea behind being pseudocode behind our assembly code is that we will first run a standardized for loop. We are going to check every single every single 32 values with each other. And then for each value, since we can't load all 16 bits, we will load each values to one. We will first compare the low 8 bits and calculate and perform XOR, and the high 8 bits and perform the XOR, and then count all these bits together, and then do the comparison. For the second program, this one wants to find the absolute distance of all pairs. This one becomes a lot more tricky because we don't have an absolute subtraction method, and if we operation, and if we did, it doesn't really actually help us in this case because once, like I said again, we are looking at 16 bits absolute difference, not 8 bits absolute difference. So what we do instead is that we first do a standard subtraction. Like before, we divide it into a high bit and a low bit, and then we do the standard instructions, and then we take a look at this thing. If after this whole calculation there's no more borrow bit, that means that borrow flag is not up. That means that this value is positive, and if it's positive, we can just take it as correct. What becomes kind of tricky is what if these are negative. Now, another thing we want to consider is that, so if these are negative, then it also isn't as hard. If the result is negative, the idea is that we would use our not instruction to simply flip it and plus 1. So flipping the sign. So this would be the standard framework if you're subtracting two numbers that are both positive. What makes this kind of tricky is that but our pairs might be signed as well. So what do we do instead? Now, for the same sign ones, you can see that if they're both positive and both negative, they both work. You simply have to subtract them, and if they're negative, you flip the sign. Now, if they're opposite signs, things become a bit tricky because now instead of subtracting, you actually want to add. So that's kind of what our algorithms does, is that we first detect if they're same sign or opposite sign. If they're same sign, we subtract both high and low, see if borrow bit is negative or positive. If the result is negative, we flip it so that's absolute. If they're a different sign, instead of doing subtraction, we add the two values together, and then we perform this same negative, and then we perform the same absolute value collection. The last one, which is the most tricky one, and the one that required our more specialized instruction, is that the 16 to 16-bit sign multiplication. What makes this very, very, very challenging is that for 16 to 16 values to multiply, the product could be 32 bits. Now remember, our registers and our data path only stores 8 bits. So 32 is way beyond what our register can store. So how do we do this? Now, in order to do this, we just first assume the output is always going to be 32 bits. We will assume that. And then we will divide this 32-bit final output into 4 different slots. The lowest slots would only be can be determined only by the low bit calculations of the two values. So we do that as same. The second, so the second lowest can be calculated by the two high of the high of the lowest, the two lowest, and the low of the highs and lows, plus the carry. And then we use this logic and so on. So essentially, we would have one register store the carries, one register storing the lows, one register storing the other lows, and register storing the high, and 2 registers doing the calculation. And after we do all that, we load that onto our memory. One thing that's also a bit complicated is that the final product is going to require a sign correction, since our multiplication methods are unsigned. And what we kind of do with this is that essentially we check in the very beginning that if the two values are negative or positive, and then we do the sign correction. After we use the sign, function to detect the sign, and then we take the branching for that. And then we basically adjust the sign after the entire output has already been calculated. So that's the main idea of the final 3 programs. It's a bit of a mouthful, but so here's more about the actual system Verilog logic. Not much to say here, and also our files. We have an instruction memory file, a data memory file, and a register file in a more a simple Quartus viewer that we compiled, and also the Python assembler, which essentially just maps these assembly snippet. This is our for program 1, and then we map them into the machine code. And that's about it. Thank you so much.